Chapter 1, Exercise 9. For the first point, show that precedes satisfies definition 1.5. For the second point, recall definition 110. Construct a subset of complex numbers lying on the imaginary axis bounded from above with respect to preceding order, which does not have a supremum in C. We need to show that the properties 1 and 2 of definition 1.5 hold for this relation. Recall that less than is an order in real numbers, and so exactly one relation in each of these two triplets is true: A less than C, A equals C, A greater than C, and B less than D, B equals D, B greater than D. First, we prove that precedes satisfies definition 1.5i. Let Z equal A plus BI and W equals C plus DI. If A less than C, then Z precedes W. If A greater than C, then W precedes Z. Hence, assume that A equals C. If B less than D, then Z precedes W. If B greater than D, then W precedes Z. If B equals D, then Z equals W. Thus, precedes satisfies definition 1.5i as only one of the statements Z precedes W, Z equals W, W precedes Z is true. Next, we show precedes satisfies definition 1.5.2. Let Z equal A plus BI, W equals C plus DI, and V equals E plus FI be complex numbers. We want to show that if Z precedes W and W precedes Z, then Z precedes V. Since Z precedes W, then either A is less than C or A equals C and B less than D. Since W precedes V, then either C is less than E or C equals E and D less than F. If A less than C and C less than E, then A is less than E, thus Z precedes V. If A less than C and C equals E, then A less than E, thus Z precedes V. If A equals C and C less than E, then A less than E, thus Z precedes V. If A equals C and C equals E, then A equals E. Since B less than D and D less than F, then B less than F. Thus, Z precedes V. Thus, precedes satisfies definition 1.5.2. For the second part, assume that complex numbers precedes has the least upper bound property. Let S equal the set of Z equals 0 plus Ni, n an integer, n greater than 0. Then S is a non-empty subset of complex numbers because I is in S. S is bounded above by any positive real number A, since if 0 is less than A, then Z equals 0 plus BI precedes A plus 0i equaling A. Let supremum of S equal A plus BI, then A greater than or equal to 0, since A plus BI is an upper bound. Assume that A greater than 0. Then A over 2 plus BI precedes A plus BI, and thus A over 2 plus BI is a smaller upper bound of S, which is a contradiction. Hence, it must be A equals 0, and so supremum S equals BI. By the Archimedean property, theorem 120a, for any b in real numbers, there exists an integer m greater than 0, such that m is bigger than b. Then, 0 plus mi is in S, and bi precedes 0 plus mi. This contradicts the fact that bi is an upper bound of S. Hence, supremum S does not exist in C, and so the least upper bound property does not hold. Note that if A, B in real numbers, then B precedes A is the same as B less than A. So the restriction of lexicographic order of complex numbers in real numbers is the usual order of real numbers. Thus, this exercise provides an example of an ordered set without the least upper bound property that contains an ordered subset with the least upper bound property. Thanks for watching.